Good day, everyone. For this video, I will discuss the topic electric field. Let me allow you to introduce myself. I am Alexis PICA, section CED 10301P, so BSED major in science. Uh, for our objectives, at the end of presentation, the audience will able to define the concept of electric field in the context of physics. Second, explain the process of calculating electric field using integrals for continuous charge distributions. Third, understand the concept of electric field due to continuous charge distribution. What is electric field? An electric field is a region of space around an electrically charged particle or object in which electric forces can be felt. It is an invisible force field that exerts a force on any other charged object placed within it. How we calculate electric field? Calculating the electric field using integration involves determining the contributions of infinitesimally small charge elements to the overall field at the point. This method is commonly employed for continuous charge distributions. So let's proceed to electric field due to continuous charge distributions. In practical situations, such as objects charged by rubbing, the average separation between source charges is small compared to their distances from the field evaluation point. This allows the system of source charges to be modeled as continuous, implying a total charge distributed continuously through a volume or surface. To evaluate the electric field of continuous charge distribution, the following procedure is used. First, we divide the charge distribution into small elements, each of which contains a small amount of charge. AQ in as you can see in the figure 1913. The electric field E at P due to a continuous charge distribution is the vector sum of fields AE due to all the elements AQI of the charge distribution. So the three sample elements are shown. Um, to calculate the electric field AE at a point P due to one these elements. Finally, we evaluate the total field at P due to the charge distribution by performing a vector sum of contributions of all the charge elements. So by applying the superposition principle. So in the first, the electric field at P in figure 1913 due to one element of charge AQ is given by whether the index I is refers to the ith elements is the distribution. R is the distance from the element to the point P, and R is the unit vector directed from the element toward P. The total uh, the total electric field E at the P due to all elements in the charge distribution is approximately. Now, we apply the model in which the charge distribution is continuous and we let the elements of charge become infinitesimally small. With the model, the total field at P in the limit AQI is to 0 becomes. So, where dq is an infinitesimal amount of charge and the integration is overall the charge creating the electric field, the integration is a vector operation and must be treated with caution. So it can be evaluated in terms of individual components, or perhaps symmetry arguments can be used to reduce it to a scalar integral. So we shall illustrate this type of calculation with several examples in which we assume that the charge is uniformly distributed on the line or a surface or throughout some volume. When the performing such as calculations, it is a convenient to use the concept of a charge density along with the following notations. Okay. So, um, where dq is an infinitesimally amount of charge, so if a total charge is q is uniformly distributed throughout the volume v, the volume charge density p is defined by p is equal to qv, where p has units of Columbus per cubic meter. So volume charge density. And if Q is uniformly distributed on a surface of area, a surface charge density O is defined by where Q has a units of Columbus per square meters. O is equal to Q over A and surface charge density. And if Q is uniformly distributed along a line of length E, or the linear charge density, is defined as unit of Columbus per minute is per meter is equal to Q over linear charge density. So linear charge density or E the length the length. Okay. So let's proceed to problem solving strategy, calculating the electric field. The following procedure is recommended for solving a problem that involve the determination of electric field due to individual charges or a charge distribution. So number one is conceptualize. Establish a mental representation of the problem. So here, we think carefully about the individual charges or the change or the charge distribution and imagine what type of electric field it would create and appeal to any symmetry in the arrangement of charge just to help you visualize the electric field. Second, categorize. Are you analyzing a group of individual charges or a question charge distribution? So the answer to these questions tell you how to proceed in the analyze step. Third is the analyze. So A, if you are analyzing a group of individual charges, use the superposition principle. When several point charges are present, the resultant field at the point in space is the vector sum of the individual fields due to the individual charges. And be very careful in the manipulation of vector quantities. It may be useful to review the material on the vector addition in uh, other example demonstrated in this procedure. B is if you are analyzing a continuous charge distributions, replace the vector sum for evaluation the total electric field from individual charges by vector integrals. The charge distribution is divided into infinitesimal pieces, and the vector sum is carried out by integrating over entire charge distribution. And number and four and the last is finalize. Check to see if your electric field expression is consistent with the mental representation and if it reflects any symmetry that you noted previously. Imagine various parameters such as distance of the observation point from the charges of the radius of any circular object to see if the mathematical result changes is a reasonable way. So that's all um, for our references.